There is a fundamental inaccuracy in the mental image most of us carry of the solar system. If you were to draw a map to scale and place the Sun in the centre and Pluto at the very edge of your paper, you would be missing roughly 99% of the actual picture. The planets Mercury, Earth, Jupiter, all the way out to Neptune, are not the defining features of our home. They are just the crowded, tiny centre, a dense knot of worlds pressed so tightly together relative to the true scope of the solar system that they barely occupy a fraction of the space that actually belongs to our star. The true boundary of the solar system sits thousands of times further out, forming a structure so enormous that it technically defines the outermost gravitational territory held by our Sun. It is called the Oort Cloud, and while the word cloud might conjure images of a soft, drifting haze, it would be far more accurate to think of it as a shell, a vast, spherical, icy enclosure that effectively surrounds everything we have ever known and locks us inside our own cosmic neighbourhood. To understand what this structure actually looks like, you have to set aside the image of the solar system that most of us learned from textbooks and classroom posters. When we examine the planets, we see a flat disk. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all orbit the Sun on roughly the same flat plane, like marbles rolling around the rim of a giant dinner plate. That image is accurate for the planetary neighbourhood, but the Oort Cloud does not follow this rule at all. It is not a ring, it is not a belt, it is a sphere. It surrounds the Sun from every conceivable direction, above, below, to the sides, behind, in front. If you could somehow observe it from the outside with the naked eye, you would see a perfect hollow bubble of ice enclosing our entire solar system. We are, in a very literal sense, living inside a massive spherical shell of frozen matter that extends in all directions without preference or boundary. The scale of this bubble is difficult to process because the numbers involved are so extraordinarily large that they quickly lose meaning. The moment you hear a number like 100,000, your brain begins to treat it as an abstract symbol rather than a real quantity. Astronomers navigate this problem by measuring these distances in units called astronomical units. One astronomical unit is the distance from the Earth to the Sun, approximately 93 million miles. That single distance, 93 million miles of empty space, is used as the base unit when talking about the solar system. For context, consider Neptune, the outermost of the 8 recognized planets. Neptune orbits the Sun at a distance of roughly 30 astronomical units. That is 30 times the distance from the Earth to the Sun, or about 2,790,000,000 miles. That is where most people assume the solar system ends. That is the edge of the planetary neighbourhood, where the last great world drifts in the cold and the dark. But the Oort Cloud belongs to a completely different category of distance. Its inner edge does not even begin until you travel somewhere between 2,000 and 5,000 astronomical units from the Sun. That means even the nearest, most modest boundary of the Oort Cloud begins at a distance 66 times greater than the orbit of Neptune. And the cloud does not stop there. It extends outward in all directions to somewhere between 50,000 and 100,000 astronomical units, based on the best current estimates available to science. To put that in perspective, 100,000 astronomical units is nearly halfway to Proxima Centauri, which is the nearest star to our Sun. The Oort Cloud does not just surround the solar system in the way a backyard fence surrounds a garden. It extends so far from home that it approaches the territory of another star entirely. We are not a planet with a few orbiting companions. We are a star, embedded deep inside a shell of frozen matter that stretches almost to the threshold of interstellar space. A physical model helps make this visceral in a way that raw numbers cannot. Imagine we scale everything down so that the distance from the Earth to the Sun becomes exactly 1 inch. At that scale, where does everything else land? Neptune, the outermost planet, would sit about 30 inches from the Sun, less than 3 feet. You could hold the entire planetary solar system in a space smaller than a doorway. The dwarf planet Pluto, whose demotion from full planetary status once felt so dramatic, would be only 40 inches away. You could comfortably fit the entire known planetary system on a large dining room table with room to spare. Now, on that exact same scale, where would the Oort Cloud begin? You would have to get up from the table, walk out of the room, and travel several hundred feet before you reached its inner edge. The outer boundary of the cloud, at 100,000 astronomical units, would sit roughly 1.5 miles away from that table. On the scale, where the entire planetary system fits comfortably on a tabletop, the Oort Cloud extends outward for 1.5 miles in every direction. The planets are not the solar system. They are a few specks of dust resting at the centre of a sphere that is several miles wide. This massive structure is not uniform. It is divided into 2 distinct regions that differ in shape, density, and character. The part closer to the planetary system is known as the Hills Cloud, or sometimes the inner Oort Cloud. Unlike the perfectly spherical outer region, the Hills Cloud is shaped more like a thick donut or a flattened disk with some puffiness to it. It retains traces of the flat geometry that governs the planetary system because it is still close enough for the Sun's gravitational influence to impose some order. This inner region contains roughly 5 times as much total mass as the outer region, compressed into a far smaller volume, which means it is significantly denser. As you travel further out from the Hills Cloud, you transition into the outer Oort Cloud, which is the vast spherical shell that envelops the entire system. This is the region that truly earns the description of a bubble. The objects out here bear no resemblance to the rocky asteroids drifting in the belt between Mars and Jupiter. They are not metallic boulders rich in iron. They are volatile ices, complex and primordial. You have frozen water, frozen methane, frozen ammonia, frozen carbon monoxide. These substances exist in a pristine, unaltered state because they have been sitting in the absolute cold of deep space for 4.5 billion years, almost entirely undisturbed. They are as close to untouched remnants of the original solar system as anything that still exists. People commonly make a specific error in their imagination when they try to visualize the Oort Cloud. The word cloud, combined with the knowledge that it contains trillions of individual objects, leads many to picture a thick blizzard of icy rocks, a dense fog of matter through which a spacecraft would have to carefully navigate. The reality is almost the complete opposite. The Oort Cloud is extraordinarily empty. Even though it may contain anywhere from 1 trillion to several trillion individual icy objects, the volume of space they occupy is so incomprehensibly vast that the average distance between any 2 of those objects is tens of millions of miles. The density of matter in the Oort Cloud is essentially 0 by any practical standard. If you were somehow transported to the surface of one of these icy bodies and looked around you, what would you see? Nothing. Not a blizzard of nearby companions, not even a faint glow from the object next to you. You would see stars, the same stars visible from Earth, but rearranged slightly because you are now in a different position. There would be no sign of the trillion other objects surrounding you at a distance of tens of millions of miles. You would not be able to see our Sun as the warm yellow disk it appears from Earth. From the outer Oort Cloud, the sun would look like nothing more than the brightest star in the sky. Brighter than everything else, certainly. But not warm, not large, not close. Just a point of fierce white light burning alone in the darkness. It is one of the most profoundly lonely environments the human mind can contemplate. A frozen rock drifting in silence, surrounded by nothing visible, orbiting a distant point of light so slowly that it completes one circuit every few million years. No sound, no movement, no companions, just the ancient cold and the indifferent stars. The natural assumption is that the Oort Cloud has always been there, that these icy bodies formed at the edge of the solar system and simply stayed put for billions of years, like geological artifacts locked in place from the beginning. This assumption is completely wrong, and the real story of how the Oort Cloud formed is far more violent and dramatic than a placid cloud of ancient ice would suggest. These trillions of icy bodies were not born at the edge of the solar system. They were born much closer to the Sun, in the same general region where the gas giants formed. In the earliest era of the solar system, when the Sun was young and the planets were still assembling themselves from swirling disks of gas and dust, the region between the orbits of Jupiter and Saturn was packed with debris. There were countless planetesimals, rocky and icy bodies of varying sizes, crowding the inner solar system and the zone around the gas giants. The building blocks of worlds were everywhere, but the early solar system was not a stable place. The gas giants, particularly Jupiter and Saturn, had not yet settled into their current stable orbits. They were migrating. Their gravitational interactions with each other and with the disk of material around the Sun caused them to shift inward toward the Sun and then outward again in a chaotic gravitational dance that lasted for tens of millions of years. As these massive planets moved through the system, their gravity acted like an enormous slingshot. Jupiter, with its overwhelming gravitational field, ploughed through the debris field of the early solar system and flung objects outward with tremendous force. Some of that debris was ejected with enough velocity to escape the Sun's gravity entirely, drifting off into interstellar space, lost forever to the solar system that created it. But a very significant portion of that ejected material did not quite reach escape velocity. It was launched outward with tremendous force, travelled to the very edge of the Sun's gravitational reach, slowed and stalled. These objects entered extremely long, slow, distant orbits. And over billions of years, another force began to shape them into the spherical structure we see today, the gravity of passing stars. As nearby stars drifted past the solar system over cosmic timescales, their gravitational influence nudged the orbits of these distant objects. The nudging was random, unpredictable, arriving from different directions over millions and billions of years, and random nudging in 3 dimensions over long timescales produces a sphere. The flat disk of the early debris field was slowly, gradually inflated and redistributed into the spherical shell we now call the Oort Cloud. The Oort Cloud is therefore not a pristine artifact that formed quietly at the edge of the solar system. It is a cosmic junkyard of construction materials that the gas giants threw away 4 billion years ago, slowly reorganized into a sphere by the gravity of distant stars. It is the evidence of chaos, of violence on a solar system scale, of enormous forces at work in the early universe that shaped everything we now see. This immense distance from the Sun creates a unique and fragile physical state for every object residing in the Oort Cloud. When you stand on Earth, the Sun's gravity is the absolute dominant force governing your existence. Every orbit, every tidal force, every planetary motion we observe is ruled by the Sun's gravitational pull. That hold is tight and reliable at our distance. But out in the Oort Cloud, the grip of the Sun is incredibly weak. Not absent, The Sun's gravity extends to the very edge of the cloud and holds these objects in their orbits, but so diluted over such enormous distances that it barely maintains control. It is so weak out there that the Sun is no longer the only significant gravitational player on the field. This is the region where the solar system begins to actively interact with the galaxy itself. The Sun's grip and the galaxy's influence are roughly comparable in their ability to affect the slow, distant, drifting objects of the outer cloud. Astronomers have a name for the galactic influence that operates at these distances. They call it the galactic tide. Just as the Moon's gravity raises tides in Earth's oceans, distorting the shape of the water by pulling it slightly toward the Moon as the Earth rotates, the mass of the Milky Way galaxy as a whole exerts a tidal force on the objects in the Oort Cloud. The dense central disk of our galaxy, the immense mass of the galactic core, the combined gravitational influence of several 100 billion stars. All of this creates a tidal force that acts on the outermost reaches of our solar system. This galactic tide is constantly fighting against the already weak gravity of the Sun. It stretches the cloud in some directions, compresses it in others, and distorts the orbits of individual objects in ways that would be impossible to observe from Earth in a human lifetime. Over millions and billions of years, this tidal force acts as a sculptor. It is actually the primary reason the Oort cloud is spherical rather than disc-shaped. The galactic tide prevents the outer objects from collapsing back into the flat plane that governs the inner solar system. It is both the force that maintains the cloud's shape and the force that threatens the cloud's stability. This balance is profoundly delicate. Because the Sun's hold on these objects is so fragile, the Oort cloud is not a fortress. It is not a solid defensive shell protecting the inner solar system. It is more like a permeable membrane, a boundary that can be penetrated and disturbed by outside forces. The Oort cloud is vulnerable. It is susceptible to interference in ways that the tightly bound inner solar system is not. The most significant source of interference comes from other stars. Our galaxy contains hundreds of billions of stars, and all of them are in motion, drifting through space on their own trajectories over cosmic timescales. Occasionally, those trajectories bring other stars close to our own. Not close in the human sense, not close enough to observe with the naked eye, but close in the astronomical sense, where close might mean a few light years instead of 4 light years. Even at those distances, a passing star exerts a measurable gravitational pull on the weakly bound objects of the Oort cloud. When a star passes within a few light years of the solar system, its gravity disturbs the cloud, it shakes the cage, it pulls individual icy objects out of their stable distant orbits and redirects them. Some are thrown outward into interstellar space, ejected from the solar system forever. But others, many others, are redirected inward back toward the Sun on new trajectories that swing them through the inner solar system. This is not a theoretical scenario. We have identified a specific star that will do exactly this. The star is called Gliese 710. It is a red dwarf currently located approximately 60 light-years from our solar system, which makes it an unremarkable neighbour by astronomical standards. But astronomers have carefully tracked its motion and calculated its trajectory with precision, and the results are striking. In approximately 1 million years, Gliese 710 will pass through the outer Oort cloud. Not past it at a safe distance, through it. Current calculations place its closest approach at roughly 13,000 astronomical units from the Sun. That is deep inside the outer Oort cloud. This is not a near miss. It is a direct hit on the outermost shell of our solar system. When Gliese 710 passes through the cloud, its gravitational influence will scatter millions possibly hundreds of millions, of individual icy objects. Many will be flung outward into interstellar space, but many more will be knocked inward, sent on new trajectories that carry them deep into the inner solar system on timescales of thousands to millions of years. The result will be a comet shower, a prolonged, sustained increase in the number of comets entering the inner solar system. This is not a shower in the ordinary sense of a brief meteor shower visible on a clear night. This is a rain of comets that will persist for potentially millions of years. The comets arriving from the Oort Cloud are long-period comets, objects on orbits so vast that they complete one circuit around the Sun over periods of thousands, tens of thousands, or even millions of years. This has implications that deserve serious consideration. Earth's history is marked by mass extinction events, moments when vast proportions of the species living on this planet were wiped out in relatively short periods. The most famous is the extinction that ended the reign of the non-avian dinosaurs 66 million years ago, caused by the impact of an object roughly 10 kilometers in diameter. The object that caused that impact may have been an asteroid from the inner solar system, but it may also have been a comet redirected inward from the Oort Cloud by exactly the kind of gravitational disturbance we are describing. Some researchers have proposed that the periodic nature of certain extinction events in Earth's geological record, events that seem to occur on cycles of tens of millions of years, might be connected to the periodic disruption of the Oort Cloud. As the solar system moves through different regions of the galactic disk over its orbit around the galaxy, it periodically passes through denser concentrations of stars or molecular clouds, creating enhanced gravitational disturbances on the Oort Cloud and sending enhanced comet showers inward. The Oort Cloud, in this view, is not merely a passive feature of our solar system. It is a mechanism that connects us to the galaxy and occasionally delivers consequences from that galactic interaction directly to Earth. Our direct knowledge of the Oort Cloud is frustratingly limited, and this is not a matter of scientific disinterest. It is a matter of fundamental physics and the nature of light itself. The objects residing in the Oort Cloud are small, most of them, a few kilometers across, some larger, many smaller, and they are extraordinarily far away. At distances of thousands to tens of thousands of astronomical units, even large objects reflect so little light that they are essentially invisible to our current telescopes. We have never directly observed an Oort Cloud object sitting undisturbed in its native environment. The only Oort Cloud objects we can see are the ones that have already been disturbed, the ones whose orbits have been redirected inward, sending them on long journeys toward the Sun. These are the long-period comets that occasionally streak across the inner solar system. When astronomers analyze a comet's trajectory and calculate its original orbit, they can sometimes determine that it originated in the Oort Cloud. That original orbit, stretched back through the mathematics, points to a home in the cold and distant dark. The study of long-period comets is therefore one of the primary ways we study the Oort Cloud indirectly. Every comet that arrives from the outer reaches, every icy visitor that develops a tail of evaporating gas as it approaches the Sun for perhaps the first and only time in its history, is a messenger from the cloud. Its composition tells us about the chemistry of the early solar system. Its orbit tells us about the structure of the cloud from which it came. Its very existence tells us that the outer solar system is not as static as it might appear. One of the most studied and beloved examples in recent memory is Comet Hale-Bopp, which became visible to the naked eye in 1997 and was one of the brightest comets of the 20th century. Analysis of its trajectory suggested it originated in the Oort Cloud, brought inward by gravitational perturbation at some point in the distant past. Its surface was remarkably pristine, a complex mixture of frozen gases and dust that had been preserved almost perfectly since the formation of the solar system 4.5 billion years ago. Looking at Hale-Bopp's composition was, in a very real sense, looking at the raw material from which the solar system itself was built. The composition of Oort Cloud comets is one of the reasons they are scientifically priceless. The conditions in the outer Oort Cloud are the most pristine in the solar system. The temperature is just a few degrees above absolute zero, around minus 270 degrees Celsius, which means chemical processes are essentially frozen in place. The objects out there have not been heated, altered, or processed by the sun in 4.5 billion years. They are time capsules. They carry the isotopic signatures, the complex organic molecules, the precise ratios of hydrogen and oxygen and carbon that existed in the cloud of gas and dust from which the solar system formed. If we could ever send a spacecraft to an undisturbed Oort Cloud Object 1 still sitting in its native environment, billions of miles from the sun, and analyze it in detail, we would essentially be reading the chemical recipe for the solar system itself. We would be able to trace the history of the elements present there back to the nebula from which the sun condensed, and possibly further back still, to the supernova explosions and stellar winds that created those elements in the first place. The Oort Cloud is not just a feature of our solar system, it is a library, and almost every book in it has never been opened. There is another peculiar feature of the Oort Cloud that defies intuition. The timescales involved in its dynamics are so vast that the cloud is essentially invisible to human observation on any timescale that a civilization can maintain. An individual object in the outer Oort Cloud might take 10 million years to complete a single orbit around the sun. The entire history of human civilization, from the earliest cave paintings to the present moment, represents less than 1/10,000th of one of those orbital periods. We are watching a system whose dynamics operate on timescales that dwarf us so completely that we cannot observe them changing. We are like mayflies trying to study the seasons by living through a single day, and yet the cloud is dynamic. It is not static. Stars pass. The galactic tide pulls. Comets are dislodged and begin their long journeys inward. The process is continuous, even if its pace is imperceptible to us. We can model it mathematically with considerable confidence using the physics of gravity and orbital mechanics that we understand well. But we cannot watch it happen in real time, because real time for the Oort Cloud means millions of years. The question of where the solar system truly ends is not as simple as pointing to the edge of the planetary system or even the outer boundary of the Oort Cloud. The answer depends entirely on what you mean by the solar system, and there are at least two very different valid answers. The first answer involves magnetism and particle physics rather than gravity. The sun is not simply a hot ball of light sitting passively in space. It is an active, energetic object that continuously expels a stream of charged particles, electrons and protons in every direction. This outward flow of charged particles is called the solar wind. The solar wind travels outward through the planetary system at speeds of hundreds of kilometers per second, passing through the orbits of all the planets, all the asteroids, all the comets, and continuing far beyond. As it travels outward, the solar wind gradually loses energy and pressure. It is expanding into an ever larger volume of space, and its density decreases with distance. Eventually, at some point well beyond the orbit of Neptune, but far short of the Oort Cloud, the outward pressure of the solar wind is no longer sufficient to overcome the inward pressure of the interstellar medium, the extremely thin gas and radiation that permeates the space between stars. At this boundary, something dramatic happens. The solar wind, which had been travelling outward at supersonic speeds, suddenly slows down below the speed of sound in the surrounding medium. This creates a shock wave, a pressure boundary where the solar wind essentially hits a wall and piles up. This boundary is called the termination shock. Voyager 1 and Voyager 2 both cross the termination shock. Voyager 1 inch 2004, Voyager 2 inches 2007, and both detected the sharp change in particle speeds and densities that confirmed the theory. Beyond the termination shock lies a turbulent region called the heliosheath, where the slowed solar wind mingles and struggles with the incoming interstellar medium in a chaotic, compressed zone. And beyond the heliosheath lies another boundary, this one even more significant. It is called the heliopause. The heliopause is the outer edge of the entire region, dominated by the Sun's magnetic field and particle output. It is the point where the solar wind, no matter how slowed and compressed, finally runs out of momentum entirely, and the interstellar medium takes over. On one side of the heliopause, the environment is shaped by our Sun. On the other side, the environment is shaped by the broader galaxy. Crossing the heliopause is, in one very meaningful sense, leaving the solar system. Voyager 1 crossed the heliopause in August of 2012. It was a historic moment, the first time a human-made object had crossed this boundary and entered interstellar space in the magnetic and particle sense. The instruments on Voyager 1 detected a sudden dramatic drop in the density of solar particles and a corresponding sharp spike in cosmic rays, which are high-energy particles that originate from outside the solar system and are normally blocked by the Sun's magnetic influence. It was, by the measure of magnetism and particles, the moment Voyager 1 left our Sun's domain. But this is only one definition of the solar system's edge, and it is, in many ways, the less fundamental one. Because magnetism and particles are not what makes the solar system a solar system. Gravity is. The solar system is fundamentally defined by the region of space where the Sun's gravity governs the motions of objects. And by that definition, the definition of gravitational dominance, the solar system does not end at the heliopause. It does not end until you reach the outer boundary of the Oort Cloud, where the Sun's gravity finally becomes too weak to hold objects in bound orbits. And by that definition, Voyager 1, even after crossing the heliopause in 2012, had barely left the front porch. At the time of that crossing, Voyager 1 was approximately 121 astronomical units from the Sun. Today, it is around 165 astronomical units away, moving at roughly 17 kilometers per second, about 38,000 miles per hour. That is an extraordinary speed by human standards. It is faster than any object humanity has ever deliberately launched. It covers 10 miles every single second. It is moving so fast that if you launched an identical spacecraft from New York, it would reach Los Angeles in less than a quarter of a second. And yet, by the standards of the Oort Cloud, Voyager 1 is essentially standing still. The inner edge of the Oort Cloud begins somewhere between 2,000 and 5,000 astronomical units from the Sun. Voyager 1, at approximately 165 astronomical units, is not even a tenth of the way to the beginning of the cloud, let alone anywhere near its outer boundary. Even travelling at its current extraordinary speed, Voyager 1 will not reach the inner edge of the Oort Cloud for somewhere between 300 and 1,000 years, depending on where that boundary is ultimately determined to lie. The exact year when it finally encounters the first of those frozen, ancient icy bodies will fall somewhere around the 23rd or 24th century, and by that point, Voyager 1 will have been dead for hundreds of years. The spacecraft is powered by a radioisotope thermoelectric generator, a device that converts the heat released by the natural radioactive decay of plutonium-238 into electrical power. This is not a fuel tank that can be refilled. The plutonium is continuously decaying, and as it decays, it produces less and less heat, which generates less and less electricity. The power output has been declining steadily since the day Voyager 1 was launched in 1977. NASA engineers have been carefully managing the spacecraft's power budget for decades, turning off instruments one by one as power becomes insufficient to run them all. Current projections suggest that Voyager 1's power supply will fall below the minimum threshold needed to operate any scientific instruments around 2030. After that point, the spacecraft will continue moving through space, but it will no longer be able to see, hear, or measure anything. It will fall silent. It will drift onward as a dead piece of metal, following the trajectory its launch gave it 47 years ago, with nobody home to record what it encounters. And it will drift in that silence for a very long time. After Voyager 1 finally goes quiet, it will take approximately 300 years to reach the inner edge of the Oort Cloud, and then it will spend roughly 30,000 years passing through the shell before emerging on the other side. 30,000 years. For context, 30,000 years ago, modern humans were painting the walls of caves in what is now France and Spain. Agriculture had not been invented. No city had ever been built. No written language existed. The entire arc of recorded human history occupies a fraction of the time that Voyager 1 will spend silently drifting through the Oort Cloud. Only when it finally emerges from the outer boundary of the cloud, if we use the gravitational definition, will Voyager 1 have truly left the solar system. Everything before that moment, including crossing the heliopause, is technically still within the extended territory of our star. This reality imposes a profound and humbling constraint on human ambitions. We have, as a civilization, spent centuries dreaming of the stars. We have written stories about interstellar travel, designed fictional, faster-than-light drives, imagined futures where humanity spreads across the galaxy the way we once spread across continents. But the Oort Cloud, silent and invisible and barely studied, represents the first true barrier to those dreams, and we cannot even come close to crossing it with the technology we currently possess. The fundamental engineering challenge begins with something called the rocket equation. In simple terms, the rocket equation describes the relationship between the speed a rocket can achieve, the mass of the rocket, and the amount of propellant it carries. The equation reveals a cruel exponential relationship. To go faster, you need more propellant. To carry more propellant, you need a bigger rocket. To move a bigger rocket, you need even more propellant, and so on in a self-defeating spiral that quickly makes the mathematics impossible. For a journey within the planetary system, this equation is challenging but manageable. We have been doing it for over 60 years. We send probes to Mars, to Jupiter, to Pluto, and beyond. But the Oort Cloud introduces a categorically different problem. The void between Neptune and the inner edge of the Oort Cloud, and then the Oort Cloud itself, is essentially a desert, an almost perfectly empty expanse with no resources, no stopping points, no places to refuel. In the inner solar system, a long-duration spacecraft can, at least theoretically, supplement its fuel supply by mining resources from nearby bodies. Robotic missions could extract water ice from asteroid surfaces, split it into hydrogen and oxygen, and use those gases as propellant. You could island hop your way through the planetary system, stopping at each convenient body to gather more fuel for the next leg. The bodies are close enough together, relatively speaking, that this strategy is plausible. But once you cross the orbit of Neptune, the islands disappear. The Oort Cloud may contain trillions of icy objects, but those trillions of objects are distributed across a volume of space so incomprehensibly vast that the average density is essentially nothing. As we have established, the average distance between two adjacent objects in the Oort cloud is on the order of tens of millions of miles, roughly the same as the distance from Earth to Saturn. You cannot hop between these objects. They are not close enough for any practical refueling strategy. You are entering a desert that is 100,000 astronomical units wide, with no oases. This means that any spacecraft attempting to cross the Oort cloud on a reasonable timescale must carry every gram of propellant it will need for the entire journey from the moment it leaves Earth. But the rocket equation tells us that to accelerate a spacecraft to speeds high enough to cross the Oort cloud in a human meaningful time, say a few thousand years, instead of 30,000, you would need to carry a quantity of propellant so enormous that it dwarfs anything humanity has ever considered building. The math does not work with chemical rockets. It does not work with conventional nuclear propulsion. Even the most optimistic projections for advanced propulsion concepts like nuclear pulse drives or laser-driven sails struggle to make the numbers add up for a crewed mission. A journey of 30,000 years is not a journey. It is a geological epoch. If we launched a crewed spacecraft today, a great arc of a ship carrying a self-sustaining community of humans, the civilization that built and launched it would likely be unrecognizable or extinct long before the ship reached the outer boundary of the Oort cloud. The crew would not merely live their entire lives in transit, their children would, their grandchildren would. Hundreds of generations of people born, living, aging and dying aboard the ship, never knowing any home other than the metal corridors of a vessel moving through absolute darkness, would pass before anyone aboard the ship could see the outer boundary of the solar system. That is not a mission. That is the entirety of civilization, compressed into a metal tube, adrift in the dark for 30,000 years. The Oort cloud, therefore, functions as a natural quarantine zone, a vast cold barrier that separates us from the rest of the galaxy more effectively than any physical wall ever could. It is not hostile in the way that a storm or a radiation belt is hostile. It is hostile simply by virtue of its scale. The barrier it presents is not one of danger, but of distance, duration, and the merciless physics of propulsion. We are, by the measure of the Oort cloud, a completely isolated civilization. Not isolated in the sense of being trapped on a single planet, though that too is true for the overwhelming majority of us. Isolated in the deeper sense that the nearest exit from our star's gravitational domain requires a journey that exceeds the entire span of human history several times over. The stars we see every night are not neighbours. They are not even distant neighbours in any meaningful sense. They are points of light separated from us by a gulf so profound that the word distance does not adequately capture it. And yet, for all its capacity to humble us, the Oort cloud is not merely an obstacle. It is a place. It has structure, history, and dynamics. It interacts with the galaxy in ways that ripple inward and occasionally touch the worlds where life exists. It is, in its own way, one of the most scientifically important regions of the solar system and one of the least explored. Understanding it more deeply is not an academic exercise. It is fundamental to understanding where we came from, how the solar system evolved, and what forces from the galaxy beyond have periodically reached in and touched the inner worlds. To appreciate the full significance of the Oort cloud in the history of life on Earth, you have to consider its role as an intermediary between the solar system and the galaxy. The galactic tide, which we have already discussed as the force that maintains the cloud's spherical shape, does not operate at a constant intensity. As the solar system travels around the center of the Milky Way, a journey that takes approximately 225 million years to complete it, passes through different regions of the galactic disk. Some regions are denser than others. Some contain more stars, more molecular clouds, more mass per unit volume. When the solar system passes through a denser region of the galactic disk, the galactic tide intensifies. The gravitational perturbations on the outer Oort cloud become stronger, and more objects are dislodged from their stable, distant orbits. More comets are redirected inward. The rate of long-period comet arrivals in the inner solar system increases. This periodic variation in the comet flux reaching Earth has been studied extensively, and some researchers have proposed that it may leave a detectable signature in the geological and paleontological record. The idea is called the galactic carousel hypothesis by some, and it connects the rhythm of the solar system's orbit around the galaxy to cycles of disruption visible in Earth's history. Every time we pass through a dense arm of the galaxy, the Oort cloud is shaken more vigorously, more comets are sent inward, and the probability of an impact on Earth increases. Over geological timescales of hundreds of millions of years, this could produce a periodic increase in the rate of large impacts on Earth, and potentially a corresponding periodic increase in mass extinction events. The evidence for this correlation is contested. Not all researchers find the periodicity convincing, and the geological record of extinctions is noisy enough that fitting a periodic pattern to it requires careful assumptions. But the mechanism itself is physically sound. The galactic tide is real. It demonstrably affects the Oort cloud. Variations in the galactic tide as we move through different regions of the galaxy are expected based on everything we know about the structure of the Milky Way. Whether those variations are large enough and regular enough to produce a measurable signal in the extinction record is an open question, but it is not a question born of speculation. It is grounded in well-established orbital mechanics and gravitational physics. What is not contested is this: the Oort cloud connects us to the galaxy. It is the interface layer through which galactic forces reach into our solar system. Without the Oort cloud, the galaxy and the solar system would be more isolated from each other than they are. With it, every passing star, every fluctuation in the galactic tide, every dense molecular cloud we drift through on our long orbit around the galactic center has the potential to send a message inward in the form of a comet. The Oort cloud is the ear that our solar system holds to the wall of the universe. The chemistry of that interface is equally fascinating. One of the most profound and unresolved questions in all of science is how life began on Earth. We know the approximate timing life appears in the geological record within a few 100 million years of Earth's formation, which is quite fast on cosmic timescales. We know the basic chemistry involved carbon-based molecules, water as a solvent, energy sources like sunlight or chemical gradients. But the specific pathway from simple chemistry to self-replicating molecules remains one of the deepest mysteries in science. One hypothesis that has gained considerable scientific attention over the decades is called panspermia, and the Oort cloud plays a central role in its most sophisticated versions. The basic idea of panspermia is that the chemical building blocks of life, or even life itself in microbial form, can travel between worlds and potentially between star systems. Carried on the surfaces of comets and asteroids, the delivery of organic molecules to early Earth by cometary impacts is not speculative, it is well-established observational fact. Comets are extraordinarily rich in organic chemistry. They contain amino acids, which are the building blocks of proteins. They contain nucleobases, which are the building blocks of DNA and RNA. They contain sugars, lipids, and a vast array of complex carbon compounds. We know this because we have studied comets directly. The European Space Agency's Rosetta mission, which orbited Comet 67P Churyumov-Gerasimenko for 2 years and landed the Philae probe on its surface in 2014, detected an extraordinary diversity of organic molecules in the comet's material. More than 70 distinct organic compounds were identified, including glycine, which is the simplest amino acid. Where do these organic molecules come from? They form in space, in the cold environments of molecular clouds and the outer solar system, through chemistry driven by ultraviolet radiation and cosmic rays acting on simple molecules like water, methane, and ammonia. The outer Oort cloud, with its cold temperatures and exposure to galactic cosmic rays, is precisely the kind of environment where complex organic chemistry can proceed slowly over billions of years. The icy objects sitting out there are not merely frozen water and simple gases. They are slowly cooking, in the cold and the dark, through radiation-driven chemistry that builds molecular complexity from simplicity. When one of these objects is dislodged from the Oort cloud and sent on an inward trajectory, it carries that accumulated chemistry with it. As it approaches the inner solar system and warms in the increasing sunlight, it releases those molecules into space. Some fraction of that material eventually reaches the surfaces of the inner planets. In the early solar system, when the rate of comet impacts was far higher than it is today, the delivery of organic molecules to young Earth was continuous and substantial. The oceans themselves may partly owe their existence to the water delivered by comets and asteroids over hundreds of millions of years. Whether life itself or the specific molecules needed for life to originate was delivered to Earth from the outer solar system is a question that cannot yet be answered definitively. But the Oort cloud is one of the most plausible reservoirs for the kind of complex organic chemistry that life requires. Every long-period comet that arrives in the inner solar system from the cold outer reaches is, in a sense, a delivery from that vast chemical library, a sample of the molecular inventory accumulated over billions of years in the most pristine environment in the solar system. The question of how we might ever study the Oort cloud directly, not indirectly, through the comets it sends inward, but through missions actually sent outward to the cloud itself, is one that has occupied the minds of mission planners and spacecraft engineers for decades. The challenges are severe enough that no mission to the Oort cloud has ever been formally approved and funded, but the scientific case for such a mission is overwhelming, and the conceptual work has been done. The first and most obvious challenge is time. At the speeds achievable by current propulsion technology, a spacecraft launched today would require hundreds of years to reach even the inner boundary of the Oort cloud. No space agency has the institutional continuity, the budget cycles, or frankly the political will to commit to a mission whose primary scientific returns would not arrive for centuries. The entire history of the modern space age spans less than a century. Committing to a mission that takes 3 centuries to reach its destination is outside the current framework of how science funding and institutional planning works. But mission architects have explored ways to make the timeline more tractable. The most promising approaches involve advanced propulsion systems that would allow spacecraft to reach much higher speeds than anything currently possible. Nuclear electric propulsion, which uses a nuclear reactor to generate electricity and power ion thrusters, could potentially accelerate a spacecraft to speeds several times greater than those achievable by chemical rockets. Solar sails, driven by powerful lasers concepts, seriously studied under the name of light sail propulsion, could theoretically accelerate small probes to a significant fraction of the speed of light over time. Though the engineering challenges are formidable, and the timescales still long. The interstellar probe concept, which has been under serious study at NASA and associated institutions for years, envisions a spacecraft capable of reaching the heliopause and the inner Oort cloud within a few decades of launch, using a combination of advanced propulsion and gravitational assists from Jupiter. Such a mission could potentially reach 200 or 300 astronomical units within 50 years. That would still not bring it to the heart of the Oort cloud, but it would take it deep into unexplored territory and provide the first direct measurements of the environment between the heliopause and the inner cloud, a region we know almost nothing about. The scientific return from even a relatively modest mission into this region would be extraordinary. We would be able to measure the particle environment directly, characterize the density and composition of the interstellar medium at those distances, study the actual boundary structure of the heliopause in ways that Voyager's aging instruments could not, and potentially detect the gravitational influence of the Oort cloud on spacecraft trajectories. We would be operating in a region of the solar system that no instrument has ever visited with any purpose-built scientific payload. Even more ambitious concepts envision robotic probes capable of actually reaching the Oort cloud and making rendezvous with individual objects, landing on them, sampling them, analysing their chemistry in situ. A probe that could reach an undisturbed Oort cloud object and conduct a detailed chemical analysis would represent one of the greatest scientific achievements in human history. It would be reading the oldest, most pristine record of the solar system's formation available anywhere. Every molecule sampled from an Oort cloud body that has never been warmed by the sun would be a direct window into the chemistry of the solar nebula 4.5 billion years ago. The technical requirements for such a mission are staggering. The probe would need to travel enormous distances in a reasonable time frame, requiring propulsion systems far beyond current capabilities. It would need to navigate to a specific object in a region we cannot directly observe, requiring targeting precision we do not currently possess. It would need to operate autonomously for decades with no real-time communication from Earth, because the round-trip light travel time to the inner Oort cloud alone would be months. And it would need to survive the journey through the interstellar medium, which bombards spacecraft with high-energy cosmic rays at rates significantly higher than those in the inner solar system. None of these challenges are insurmountable in principle. They require technology that does not yet exist, but they do not require physics that does not yet exist. The laws of nature do not prohibit reaching the Oort cloud. They merely impose enormous practical obstacles, and the history of science and technology is a history of overcoming obstacles that once seemed impossible. A person living in 1850 would have considered putting a machine on the moon to be a fantasy. A person living in 1920 would have considered the Voyager missions to be science fiction. The Oort cloud may represent the next horizon whose crossing, when it finally comes, will be regarded as the moment humanity became genuinely capable of exploring the solar system in full. There is a particular object in the solar system that has done more than almost any other to reshape our understanding of what lies between the planetary system and the Oort cloud. Its name is Sedna, and its discovery in 2003 was a genuine surprise. Sedna is a small world, perhaps about 1,000 kilometers in diameter, making it roughly half the size of Pluto. Its surface is deep red, one of the reddest objects in the solar system, colored by complex organic molecules called tholins that form when simple carbon compounds are exposed to radiation over long timescales. What makes Sedna remarkable is its orbit. Its closest approach to the Sun, a point called perihelion, is approximately 76 astronomical units. That is already well beyond Neptune. But its most distant point aphelion is approximately 937 astronomical units from the Sun. Its orbital period is approximately 11,000 years. Sedna spends the vast majority of its existence in the cold, dark outer reaches of the solar system, and its orbit brings it no closer to the planets than 76 astronomical units, even at its nearest approach. This orbit does not fit neatly into any of the established categories of solar system objects. It is too distant to be a Kuiper belt object. It is too close, and its orbit is too elliptical to be a true Oort Cloud object. It sits in a previously uncharted region between the two, in a zone that some researchers have informally called the inner Oort Cloud, or, in recognition of Sedna's unique status as the first object found there, the Sednoid region. What could have given Sedna such an unusual orbit? Several hypotheses have been proposed, and none has been definitively confirmed. One possibility is that a passing star in the early solar system, when the Sun was still part of its birth cluster of young stars, gravitationally perturbed Sedna's orbit into its current extreme configuration. Another possibility is that a distant, undiscovered large planet in the outer solar system is gravitationally shepherding Sedna and similar objects into these unusual orbits. A third possibility involves the Sun's birth environment. The young Sun may have passed close to other forming stars and captured some of their planetesimals, which then settled into the kind of extreme distant orbit that Sedna occupies. Since Sedna's discovery, a small number of similar objects have been found in the same orbital neighbourhood, each with extreme orbits that suggest a common dynamical cause. The pattern in their orbital alignments has led some researchers to propose the existence of a large, undiscovered planet in the distant outer solar system, a world sometimes informally called Planet 9, whose gravity would explain the clustering of these extreme orbits. Planet 9, if it exists, would be a world perhaps 5 to 10 times the mass of Earth, orbiting the Sun at hundreds or thousands of astronomical units, permanently hidden from current telescopes by its extreme distance, and the fact that it would reflect only a tiny fraction of the Sun's already faint light at such distances. The search for Planet 9 has been ongoing since the hypothesis was formally proposed in 2016. Multiple research teams have been scanning the sky with powerful telescopes, looking for the faint moving point of light that would indicate a large distant world. As of now, no confirmed detection has been made. The hypothesis remains possible but unconfirmed. The pattern of extreme orbits could have alternative explanations. But the search continues, driven by the straightforward logic that if Planet 9 exists, it would be the most significant discovery in planetary astronomy in decades, and it would fundamentally reshape our model of the outer solar system. Whether or not Planet 9 exists, the discovery of Sedna and its orbital cousins tells us something important. The outer solar system, in the vast empty region between the Kuiper belt and the Oort Cloud, is not simply empty space with a few lost objects drifting through it. It has structure. It has populations of objects whose orbits were shaped by dynamic processes in the early solar system. The boundary between the Kuiper belt and the Oort Cloud is not a sharp line, but a gradual transition populated by objects whose histories record the most violent early dynamics of the planetary system. Every new object discovered in this region is a data point in a map we are only beginning to draw. Each one tells us something about the forces that shaped the outer solar system billions of years ago. And the more we understand about those forces, the better we understand the origin and evolution of the entire solar system, including the conditions that made it possible for a rocky inner planet to develop stable oceans, a breathable atmosphere, and ultimately, life. The outer solar system, is not merely a dead zone of frozen leftovers, it is a record. And like all records, it rewards those who learn to read it. The Oort Cloud's role in the history of Earth is not limited to the delivery of water and organic chemistry. The cloud also serves as the origin point for some of the most visually spectacular phenomena observable in the night sky. Long-period comets, those with orbital periods greater than 200 years, are almost universally thought to originate in the Oort Cloud. When one of these objects is dislodged from its distant home and begins its long journey inward, it travels for thousands of years before the sun's warmth begins to have any effect on it. As it approaches within a few astronomical units of the sun, the temperature rises enough to begin sublimating the surface ices. Frozen gases, water vapor, carbon dioxide, carbon monoxide, methane erupt from the surface in jets and geysers, carrying dust particles with them into space. This outgassing forms a cloud of gas and dust around the nucleus, called the coma, which can grow to enormous sizes, sometimes larger than the entire planet Jupiter. The solar wind and radiation pressure then push the coma material away from the comet, forming the characteristic tails that can stretch for tens of millions of miles across the sky. The most spectacular comets in recorded history have almost all been long-period visitors from the Oort Cloud. Comet Neowise in 2020 was visible to the naked eye from Earth and produced spectacular photographs with a bright nucleus and a long sweeping tail, visible even from light-polluted cities. Comet Hale-Bopp in 1997 was bright enough to observe with the naked eye, even from moderately light-polluted locations, and was visible for an extraordinary 18 months, a record for naked eye visibility. The Great Comet of 1997, as Hale-Bopp was sometimes called, traced its origin back to the Oort Cloud and was making, as far as astronomers could determine, one of its first close passes by the inner solar system. Its surface was essentially untouched. When a comet completes its first pass through the inner solar system and swings around the Sun, two possible fates await it. If the gravitational influence of the planets, particularly Jupiter, alters its orbit significantly, it may be captured into a shorter period orbit, becoming a periodic comet that returns to the inner solar system on a time scale of decades rather than thousands of years. These short-period comets, like the famous Halley's Comet with its 76-year period, have been processed by repeated close approaches to the Sun. Their surfaces have been heated and degassed many times. The most volatile ices have largely escaped, and what remains is a dirtier, more refractory object, a nucleus crusted with dark organic material, more asteroid-like in character than the pristine ice of an Oort Cloud body on its first visit. If the comet's orbit is not significantly altered by a first pass, it returns to the outer solar system and continues on its original trajectory, potentially not returning to the inner solar system for another 10,000 or 50,000 years. On each successive visit, the Sun strips away more of the volatile surface material. Eventually, after enough visits, a comet may become entirely depleted of the ices that drive its activity and leave only a dark, inert, rocky nucleus drifting silently through the inner solar system, indistinguishable, in some cases, from a regular asteroid. This process represents one of the mechanisms by which the Oort Cloud gradually depletes itself. Each comet redirected inward by a gravitational perturbation is either lost to the inner solar system, destroyed in a collision, or eventually ground down to inert rock. The total population of the Oort Cloud is declining on these cosmic timescales, reduced by every perturbation that sends objects inward. The population is replenished only slowly, as new objects are occasionally nudged outward from the Kuiper belt and sent into distant orbits. The Oort Cloud is not an eternal, unchanging structure. It is a reservoir with both inflows and outflows, and its current state reflects the balance of those flows over 4.5 billion years. There is a remarkable fact embedded in the dynamics of long-period comet arrivals that carries implications for the history of life on Earth. When a truly fresh Oort Cloud Comet 1, making its first pass through the inner solar system, arrives near Earth, it is a pristine object that has been chemically preserved for billions of years. But its behaviour, as it approaches the Sun, is not entirely predictable. The outgassing of volatile ices can be irregular and intense, driven by pockets of highly volatile material suddenly exposed to sunlight. The comet's trajectory can be subtly altered by these outgassing jets, which act like rocket thrusters. This is why predicting the brightness of a newly discovered comet is notoriously difficult. Astronomers have a saying, "Comets are like cats. They have tails, and they do whatever they want." A comet that looks promising weeks before its closest approach may suddenly outburst and become spectacular, or may fragment under tidal stresses from the Sun, or may simply fail to brighten as expected because its particular mix of volatile and non-volatile materials behaves differently than anticipated. The famous comet Ison in 2013 was anticipated to be one of the brightest comets of the modern era, potentially visible in broad daylight. It was a dynamically new Comet 1 that appeared to be making its first pass through the inner solar system, and its early brightness suggested it would be extraordinary. Instead, it disintegrated during its closest approach to the Sun, and essentially ceased to exist as a coherent object. The surviving fragments quickly faded, and the great comet that had been so eagerly anticipated never arrived. Ison's failure was not an anomaly. It reflected the genuine unpredictability of these ancient, fragile travellers making their first encounter with the Sun's intense heat. What Ison and every other long-period comet represent, regardless of their ultimate behaviour, is a direct messenger from the Oort Cloud, a sample of the outer solar system delivered to the doorstep of the inner worlds. The fact that these objects carry such rich organic chemistry, accumulated over billions of years in the cold outer reaches, gives them a significance beyond their spectacular visual displays. They are, in every sense of the word, letters from the beginning of time. The question of what the Oort Cloud tells us about the formation of solar systems in general is one of the most exciting frontiers in current astrophysical research. We now know, from decades of exoplanet research, that planetary systems are not rare. They appear to be common around stars. But the architecture of those systems, how the planets are arranged, how large they are, how eccentric their orbits are, varies enormously from system to system. Our solar system, with its small rocky inner planets and large gas giants in the outer system, is just one of many possible configurations. What we do not yet know is whether other solar systems have Oort Cloud analogues. Do other stars develop vast spherical shells of icy bodies at the edges of their gravitational domains? The physics suggests they should, if their systems went through the same kind of giant planet migration and debris ejection that shaped our own Oort Cloud. But detecting such structures around other stars is essentially impossible with current technology. For the same reason, we cannot directly observe our own Oort Cloud. The objects are too small, too cold, and too far away to reflect enough light to be detectable. What we can observe, indirectly, are the comets that such clouds produce. When a star passes another star closely, the resulting gravitational perturbations can send comets inward from any Oort Cloud analogue, and if those comets travel far enough, if they are ejected with enough velocity, they can actually leave their home solar system entirely and travel through interstellar space. These are called interstellar objects, and until recently, They were entirely hypothetical. In 2017, that changed. An object called Oumuamua was detected by the Pan-STARRS telescope in Hawaii, moving through the inner solar system on a trajectory that was unmistakably hyperbolic, meaning it was moving too fast to be in orbit around the Sun and was clearly passing through from elsewhere. Oumuamua was the first confirmed interstellar object ever detected visiting our solar system. Its origin was definitively outside our solar system, and the most likely explanation is that it was a fragment of material ejected from another star system, possibly from an Oort Cloud analogue around another star, perhaps billions of years ago. Oumuamua was a strange object. It was highly elongated, perhaps 10 times as long as it was wide. An unusual shape, unlike any solar system object we had previously encountered. It showed a non-gravitational acceleration as it left the inner solar system. It was speeding up slightly more than gravity alone could explain, which led to a range of proposed explanations, from the mundane to the less than extraordinary. The most conventional explanation is that it was accelerated by outgassing of volatile material from its surface, similar to the way comets are thrust by their own sublimating ices. A more speculative explanation, which received enormous public attention, was that it might be an artificial object of extraterrestrial origin. Detailed analysis of its behaviour ultimately favoured natural explanations, but Oumuamua's unusual properties have not been fully explained to everyone's satisfaction, and it remains one of the most intriguing objects ever observed passing through the solar system. In 2019, a second confirmed interstellar object was detected, Comet Borisov. Unlike Oumuamua, Borisov looked and behaved much like a normal comet. It had a coma, it showed outgassing, and its composition appeared broadly similar to solar system comets. Its interstellar origin was confirmed by its trajectory, but its similarity to familiar comets was reassuring. It suggested that at least some Oort Cloud analogues around other stars produce objects chemically similar to our own comets, implying that the chemistry of comet formation may be broadly consistent across different solar systems. The detection of two interstellar objects within just 2 years of each other, in the era of modern wide-field sky surveys capable of detecting small, fast-moving objects for the first time, suggests that interstellar visitors may be far more common than previously assumed. Statistical estimates based on those detections suggest that at any given time, perhaps thousands of interstellar objects are passing through the solar system undetected, simply too small or too dark to be seen by current instruments. Future telescopes like the Vera-C, Rubin Observatory, with its unprecedented sky survey capabilities, are expected to detect interstellar objects on a regular basis once it reaches full operational capacity. This possibility reshapes how we think about the Oort Cloud and its relationship to the broader galaxy. If interstellar objects are common, then the exchange of material between solar systems, including the organic chemistry and potentially the biological precursors carried on cometary surfaces, is not rare. It is routine. The galaxy is not a collection of isolated solar systems, each evolving independently in perfect chemical isolation. It is a system in which material flows between stars over cosmic timescales, carried on interstellar comets and fragments of Oort Cloud analogues. The chemistry of life may not have originated independently on Earth from purely local materials. Some fraction of the molecular inventory that led to life here may have arrived from another star system entirely, hitchhiking on an interstellar traveller that passed through our solar system billions of years ago. This is a possibility that once belonged to the realm of philosophical speculation and has now entered the domain of serious scientific inquiry. The detection of interstellar objects Combined with our growing understanding of the rich organic chemistry of comets and the role of the Oort Cloud as a source of those comets, has connected threads that once seemed unrelated. The origin of life, the structure of the outer solar system, the dynamics of the Milky Way galaxy, and the exchange of material between stars are all part of the same interconnected story. The Oort Cloud is not merely a peripheral feature of our solar system. It is the place where our solar system touches the galaxy. It is the membrane through which galactic influences enter and through which solar system material occasionally escapes. It is the source of some of the most chemically complex and scientifically valuable objects we can observe with current technology. And it is, in the deepest sense, the boundary that defines us, the line between what is ours and what belongs to the cosmos at large. The human impulse to explore boundaries is ancient and powerful. It drove our ancestors out of Africa and across continents. It drove navigators into unmapped oceans. It drove engineers to build machines that could leave the surface of Earth and travel to other worlds. The Oort Cloud is the next great boundary, not the next boundary in the near future, not the next boundary in any lifetime currently alive, but the next boundary in the arc of what humanity might eventually become. The timescales involved are humbling, but they are not infinite. The laws of physics do not prohibit reaching the Oort Cloud. They do not prohibit building propulsion systems capable of crossing it in timeframes that a civilization, not an individual, but a civilization could plan for and execute. They do not prohibit the eventual construction of spacecraft capable of making rendezvous with undisturbed Oort Cloud objects and returning their secrets to scientists who may live thousands of years from now. The obstacle is not impossibility. The obstacle is scale, and scale is something that technology has a consistent history of overcoming. The ocean that once separated continents and made them seem forever unreachable now takes hours to cross by aircraft. The void between Earth and the Moon, which once represented the absolute limit of human ambition, was crossed on a machine built with 1960s technology. The outer planets, which were once nothing more than points of light in the telescope, have been visited by robotic ambassadors that sent back detailed photographs and atmospheric measurements. Each of these achievements required not just technology, but the willingness to commit to a vision on timescales that exceeded any individual career or any single political administration. The Oort Cloud will require the same willingness, extended to timescales that exceed individual lifetimes. It will require civilizational commitment rather than programmatic commitment. It will require a continuity of purpose and ambition that human civilization has not yet demonstrated on such long timescales. Whether we are capable of that kind of sustained commitment across generations and centuries is, in some sense, the deepest question that the Oort Cloud poses to us. The cloud does not care about our political cycles, or our budget constraints, or our tendency to lose interest in long-duration projects when they do not produce quick results. It sits out there in the cold and the dark, 4.5 billion years old and immense beyond easy comprehension, waiting with perfect indifference for the day when something warm and curious and purposeful arrives at its threshold. Whether that day comes in 300 years or 3,000, it will mark a genuine turning point in the history of intelligence in this solar system. It will be the day when the solar system, in the truest gravitational sense, is no longer unexplored. There is a version of the future in which the Oort Cloud is not merely a boundary, but a destination. A version in which the icy bodies drifting in the outer dark are not obstacles but resources, not mysteries but known quantities, catalogued and studied and occasionally visited by machines and perhaps eventually by people. a version in which the shell that surrounds us is not a cage but a frontier, in the same way that the open ocean was once a frontier for civilizations that had only ever known their own coastlines. That version of the future is not guaranteed. It may not arrive for thousands of years. It may, in the darkest scenarios, never arrive at all if something catastrophic interrupts the long arc of technological progress before we develop the means to cross the void between the planets and the cloud. But it is physically possible. And the fact that it is physically possible means it is worth understanding in detail, worth mapping the obstacles, worth quantifying the challenges, worth dreaming about with the rigor that science demands. To reach the Oort Cloud in a time frame shorter than geological, we would need propulsion systems that operate on principles fundamentally different from the chemical rockets that have carried every human and every human-built machine into space so far. Chemical rockets release energy by burning propellant, combining fuel and oxidizer in an exothermic reaction, and expelling the hot exhaust to generate thrust. The energy density of chemical propellants is fixed by chemistry, and it is not nearly high enough to achieve the speeds needed for practical interstellar scale travel. Burning more propellant gives you more thrust, but the rocket equation punishes you for every kilogram of propellant you carry, because that propellant itself has mass that must be accelerated, requiring yet more propellant in a spiral that quickly becomes self-defeating. The next step beyond chemical propulsion in terms of energy density is nuclear propulsion. Nuclear reactions release roughly 1,000,000 times more energy per kilogram of fuel than chemical reactions. A nuclear thermal rocket, which uses a reactor to heat a propellant like liquid hydrogen to extreme temperatures before expelling it, could achieve exhaust velocities roughly twice those of the best chemical rockets. That would meaningfully reduce travel times in the inner solar system, but the improvement is not large enough to make Oort Cloud missions practical on human timescales. You would reduce the journey from 30,000 years to something like 15,000 years, an improvement that is irrelevant in any practical sense. More ambitious are nuclear pulse propulsion concepts, which involve detonating a series of small nuclear devices behind the spacecraft and riding the pressure wave of each explosion. Studies conducted under the classified Project Orion in the late 1950s and early 1960s concluded that a spacecraft the size of a city block, powered by thousands of nuclear pulse units, could theoretically accelerate to several percent of the speed of light. At 5% of the speed of light, a spacecraft could cross the inner Oort cloud in a few decades. At 10%, a trip through the entire cloud could be accomplished within a century. The physics works. The engineering, on the scale required, remains far beyond anything humanity has attempted. Beyond nuclear propulsion lies the domain of directed energy using powerful lasers or microwave beams to accelerate a spacecraft rather than carrying the energy source on board. This approach sidesteps the rocket equation entirely because the propulsion energy is not carried on the spacecraft. It stays behind, generated by a powerful transmitter in the inner solar system, and is beamed outward to a lightweight sail attached to the probe. As long as the beam can be precisely focused on the sail over astronomical distances, which requires extraordinary precision optics, the spacecraft can continue to accelerate without carrying any propellant at all. The Breakthrough Starshot initiative, announced in 2016, proposed a version of this concept aimed not at the Oort cloud, but at Proxima Centauri, the nearest star. The concept involves launching gram-scale probes equipped with miniaturized instruments and laser sails, accelerating them to 20% of the speed of light using a ground-based laser array of enormous power, and flying them past the target in a brief but information-rich transit. At 20% of the speed of light, such a probe could cross the entire Oort cloud in less than 2 years. The engineering challenges are immense. building a laser array powerful enough to accelerate even a gram-scale probe to 20% of the speed of light requires technology that does not yet exist at the required scale. Pointing that laser with sufficient precision to keep it focused on a tiny sail at distances of thousands of astronomical units is an optics problem of extraordinary difficulty. Surviving the journey through the interstellar medium at that speed, where even tiny dust particles deliver enormous kinetic energy impacts, requires shielding solutions not yet developed. And receiving useful data from a probe moving at 20% of the speed of light, broadcasting across those distances with instruments that weigh a gram, pushes the boundaries of communication technology far beyond current capability. But none of these challenges are violations of known physics. They are engineering problems, problems of precision, scale, and materials rather than fundamental barriers. The history of technology is the history of converting engineering problems from impossible to merely difficult, and then from difficult to solved. The laser sail concept represents the most plausible currently proposed pathway to crossing the Oort Cloud within a human-relevant timeframe, not for a crewed mission, but for robotic probes capable of returning information. A different approach, one that sacrifices speed for the ability to carry meaningful scientific payloads, involves what engineers sometimes call a nuclear electric mission architecture. A nuclear reactor aboard the spacecraft generates electrical power which drives ion thrusters engines that accelerate ionized gas to very high exhaust velocities using electric fields. Ion thrusters produce very low thrust compared to chemical rockets, but they operate continuously over years and decades, gradually accumulating velocity in a way that chemical engines cannot. The Dawn spacecraft, which visited the asteroid Vesta and the dwarf planet Ceres, used ion propulsion to navigate the asteroid belt in ways that would have been impossible with chemical propulsion alone. A nuclear electric spacecraft designed for the outer solar system could potentially reach the inner Oort Cloud within 50 to 100 years, carrying a suite of scientific instruments sophisticated enough to make meaningful measurements. It would not be fast by the standards of crude interplanetary travel. It would require generational commitment from the institutions that funded and built it. But it is the kind of mission that is conceivably within the technical reach of the 22nd century, if not the 21st. The scientific payload for such a mission would be extraordinary in its scope. Instruments to measure the particle environment and magnetic field structure at those distances would give us the first direct measurements of the transition zone between the heliosphere and the interstellar medium. Cameras and spectrometers to search for and characterize individual Oort Cloud objects would allow us to study their surfaces and compositions without waiting for them to be gravitationally redirected toward the Sun. Dust detectors would measure the density and composition of the interstellar medium at those distances with unprecedented precision. Gravitational sensors could potentially detect subtle anomalies in the outer solar system that might point toward undiscovered large bodies, helping settle the question of whether Planet 9 exists. Beyond the scientific return, the symbolic value of such a mission would be immense. It would represent the first time humanity had deliberately sent an explorer to the outermost reaches of the solar system with the specific intention of studying the boundary of our home. Every previous mission that reached the outer solar system did so as a consequence of trajectories designed to study the planet's voyager's journey into deep space was a bonus, not the primary goal. A dedicated Oort Cloud mission would be a statement of intent. It would say, clearly, and in the language of engineering and funding and mission architecture, that humanity intends to know its own home in full, not just the warm, in a region near the Sun, but the vast, cold periphery that makes up the overwhelming majority of the solar system's volume. The question of what we might find in the Oort cloud, beyond what we already expect to find, is one that serious scientists approach with appropriate caution but genuine curiosity. Science has a consistent history of discovering that the universe is stranger and more interesting than any prior model predicted. The solar system, which once seemed like a well-understood arrangement of planets and moons following predictable orbits, has surprised us repeatedly. The discovery of Pluto was a surprise. The discovery of the Kuiper Belt was a surprise. The discovery of Sedna was a surprise. The detection of Oumuamua was a surprise. Every time we have looked at a new region of the solar system with new instruments, we have found something we did not predict. There is no reason to suppose the Oort cloud will be different. The models we use to understand it are based on indirect evidence, the trajectories of long-period comets, the dynamics of Oort cloud analogues in computer simulations, the physics of galactic tidal forces and stellar perturbations. These models are well grounded, but they are models. They make predictions, and some of those predictions will turn out to be wrong. The actual Oort cloud may have structural features we have not anticipated. It may contain populations of objects with unusual compositions or orbital characteristics that current theory does not predict. It may show evidence of past stellar encounters that we have not yet identified from the comet record. There is also the possibility, small but not negligible, that the Oort cloud contains objects that did not originate in our solar system at all. The detection of Oumuamua and Comet Borisov demonstrated that interstellar objects do pass through the inner solar system. But those objects were passing through, they were not captured into bound orbits. There is, however, a mechanism by which some interstellar objects could be captured. During the early solar system, when the Sun was still part of its birth cluster of young stars, the gravitational environment was complex. Stars were close together. Encounters between forming planetary systems were more frequent. In that early chaotic environment, some objects from neighbouring young stellar systems could potentially have been gravitationally captured into orbits within our solar system. If any such captured interstellar objects exist today, they would most likely be found in the Oort cloud, where the weak gravity of the distant Sun could have held them in extremely long, slow orbits for billions of years. An Oort cloud object with an unusual chemical composition, one that does not match the isotopic and molecular signatures expected from solar system formation, might be exactly such a captured interstellar traveller, a piece of another star's planetary system that has been orbiting our Sun for 4 billion years. Finding such an object would be one of the most extraordinary discoveries in the history of planetary science. It would be, in a very literal sense, a sample from another star delivered to our doorstep by the gravitational dynamics of the early solar system. The concept of the solar system as a closed, isolated system which underlies so much of our intuitive picture of it is not entirely accurate. The Oort cloud is the place where that closure is most obviously incomplete. It is the region where the solar system leaks. Objects escape from it into interstellar space when they are given enough velocity by gravitational perturbations. Objects from other systems can potentially enter it. Galactic forces reach in and rearrange it. Passing stars drive through it. It is the most permeable, the most connected to the galaxy, the most cosmically integrated region of our home system. This permeability has deep implications for how we think about the solar system's place in the galaxy. The Milky Way is not a collection of isolated bubbles, each star system sealed off from all others, evolving independently. It is a dynamic environment in which material flows, in which solar systems interact gravitationally over long timescales, in which the passage of stars through each other's outer domains regularly reshuffles the cold material at the periphery. The galaxy is stirring its contents continuously, on timescales too slow for any individual civilization to observe directly but fast enough to be significant over the age of the solar system. We are embedded in that stirring. Our Oort Cloud participates in it. Every million years or so, a star passes close enough to shake the cloud and redirect some of its contents. Every few 100 million years, the solar system's orbit around the galaxy carries it through a denser region of the galactic disk, intensifying the perturbations. Every once, in a very long while, one of the objects redirected inward by these disturbances reaches Earth and delivers its payload of ancient chemistry to the surface of a living world. This is the story of the Oort Cloud told at its largest scale. Not just the story of a shell of ice at the edge of the solar system, but the story of how a solar system participates in the life of a galaxy. How the material from one epoch and one place gets redistributed across time and space. How the cold remnants of the birth of our star become the messengers that connect us to the broader cosmos. There is something profoundly moving about this picture when you sit with it long enough. Consider what an Oort Cloud object actually is. It is a body of ice and organic molecules, perhaps a few kilometers across, that formed in the disk of gas and dust surrounding the young sun 4.5 billion years ago. In its first few million years of existence, it drifted through the same region of space where the giant planets were forming, tumbling through a cosmic construction yard of epic scale. Then one of those forming giants, Jupiter, most likely, already immense with its atmosphere of hydrogen and helium, came close enough to fling it outward with a gravitational kick that sent it on a journey of billions of miles. It travelled outward for millions of years, slowing as it went, the sun's gravity gradually bleeding off its velocity. Eventually, it stalled, hundreds or thousands of astronomical units from the warmth it had briefly known, and settled into the extraordinary slow orbit that would define its existence for the next 4 billion years. It has orbited the Sun perhaps a few hundred times since then, each orbit taking millions of years, each orbit essentially identical to the last. Nothing has touched it, nothing has warmed it. It has sat in the cold and the dark, a few degrees above absolute zero, while entire species evolved and went extinct on the third planet inward, while continents drifted and mountains rose and fell, while the atmosphere changed composition and the oceans changed chemistry. And eventually, something remarkable happened. Something warm and alive and curious looked outward and began to ask questions about the darkness. That object, drifting in its ancient orbit, carries in its ice the chemical record of the solar system's birth. It carries organic molecules complex enough to be the precursors of life. It carries isotopic ratios that tell a story of stellar nucleosynthesis from before our solar system existed. The elemental legacy of stars that lived and died billions of years before our sun was born, whose supernova explosions seeded the molecular cloud that eventually collapsed to form our solar system. It is a time capsule more perfect than anything human civilization has ever created, a record more complete than any archive. It has been sitting in the cold, waiting for longer than the Earth has existed. Voyager 1 is heading toward it, not quickly, not in any time frame a human or a human institution can meaningfully anticipate, but heading toward it nonetheless. The spacecraft that launched on the 5th of September 1977, carrying a golden record of human sounds and images, travelling now in silence after its instruments fall quiet around 2030, will drift through the cold dark for centuries and then enter the Oort Cloud and spend 30,000 years crossing it. It will drift past those ancient icy bodies, perhaps within tens of millions of miles of some of them, close by Oort Cloud standards, though close by nothing else, and then emerge on the other side into the interstellar medium proper. The golden record aboard Voyager 1 is one of the most poignant artifacts humanity has ever created. It contains sounds of earth, rain, surf, wind, the calls of birds and whales and frogs, the sounds of human industry and celebration. It contains music from across human cultures and eras, selected by a committee that included Carl Sagan and Anne Druyan. It contains greetings in 55 languages. It contains images, photographs of humans, of landscapes, of scientific diagrams, of the solar system. It was designed as a message to any intelligent civilization that might eventually find the spacecraft, billions of years from now, after the Sun has long since expanded into a red giant and consumed the inner planets. There is something that transcends easy description in the image of that small metal object, 47 years old now, and falling silent, less than 200 astronomical units from the Sun that created the civilization that built it, beginning the long drift toward the Oort Cloud that will occupy the next 3 centuries of its existence. It is the furthest thing humanity has ever made go. It is the most alone any human creation has ever been, and it is carrying, pressed into a gold-plated copper disc, the sounds of a living world, moving through the silence of the outer solar system toward the ancient ice that has been waiting there since before life on Earth began. If there is a single image that captures both the smallness and the ambition of intelligent life in this universe, that might be it. A tiny machine, slower than a bullet by cosmic standards, carrying the sounds of wind and laughter and music through a silence so complete and a darkness so absolute that no human mind can genuinely imagine it. Aimed by the trajectory of its long journey at the shell of ancient ice that marks the boundary of home, the Oort Cloud, for all its scientific richness and its role in the dynamics of the solar system and the history of life on Earth, is ultimately something simpler and more resonant than any of those functions. It is the horizon. It is the edge of the known. It is the place where the light from our sun becomes just another point in the sky, and the ice of the outer solar system drifts in the cold, and the galaxy begins, and everything beyond is not yet ours. Every civilization in history has had a horizon. For our earliest ancestors, it was the edge of the valley, the far bank of the river, the line where the sea met the sky. For the navigators of the age of exploration, it was the unknown ocean, the unmapped coastline, the continent whose existence was inferred from currents and birds, and the behavior of clouds. For the first generation of space explorers, it was the atmosphere itself, the vacuum above, the moon, the planets. Each horizon, when finally reached, revealed not an ending, but a new and larger horizon beyond. The Oort Cloud is the next horizon. It is larger than any previous one. The gap between it and us is wider than any ocean, and emptier than any desert, and colder than any winter any human has ever known. It will not be reached quickly. It will not be reached easily. It may not be reached within the lifetime of anyone alive today, or anyone their children will know, or anyone their grandchildren will know, but it will be reached, because that is what intelligence does with horizons. It moves toward them, slowly at first, then faster, then all at once, in the way that impossible things have always eventually been accomplished, by creatures stubborn and curious enough to keep asking why and how and what lies beyond. The Oort Cloud waits with the perfect patience of cold and ancient things. It has been waiting for 4.5 billion years. It can wait a little longer. Meanwhile, the the Sun continues to hold it in its gentle and improbable gravitational embrace. The galactic tide continues to shape it from outside. Passing stars continue, on their million-year timescales, to shake it loose one comet at a time. And from somewhere deep inside, from the warm and noisy and improbable cluster of worlds at the center of the shell, something small and warm and bright looks outward into the dark and wonders what is out there. That wondering, that refusal to accept the horizon as a permanent boundary, is itself the answer to the question the Oort Cloud poses. The question is whether we are capable of committing to the scale of our own solar system, of taking seriously the full three-dimensional volume of space that belongs to our star, of planning and building and imagining on timescales that exceed any human life. The answer, in the cumulative evidence of everything our civilization has achieved since it first looked up at the night sky and started asking questions, is yes. Not easily, not quickly, not without failure and loss and long periods of apparent stillness. But yes, the Oort Cloud is the beginning of the end of our neighbourhood. It is the dark horizon where the familiar fades and the unknown begins. It is the vast and silent moat that keeps the galaxy at arm's length and keeps us, for now, inside the warmth and the gravity of our star. But moats have always eventually been crossed. And this one, ancient and cold and immense as it is, will be no different. Somewhere out there, in the silence and the ice, the first human-made object is drifting toward it, not yet arrived, not yet close, already silent, already dark, carrying in its gold-plated record the sounds of everything we are and everything we were and everything we loved. And beyond the shell, the stars,